Hello and welcome to this lecture on modeling the diffusion of nutrient and growth factors in biological tissues. In this session, we will explore how to model the movement and interaction of nutrients and growth factors within biological tissues using partial differential equations, specifically Fick's second law of diffusion. Understanding this process is crucial for various applications in biological and medical sciences, such as tissue engineering, drug delivery, and cancer research. We will be utilizing MATLAB's PDEPE function to solve these partial differential equations. Our approach will include following steps. Very first, defining the diffusion equation and its component. In the second level, simplifying the equation for a one-dimensional model. Then after implementing the solutions in MATLAB. When we will implement the MATLAB, we have some steps. In the very first, define the PDE function. Then we need to setting the initial concentration profile. Then after we will specifying boundary conditions. Then after solving the partial differential equation over the spatial domain and time span. And at the end, visualizing the results with the surface plots. Throughout this lecture, I will guide you through each step, providing clear explanation and MATLAB code examples. By the end of this session, you will have a solid understanding of how to set up and solve diffusion problem in biological tissues using MATLAB. Let's get started. So here we are going to discuss about the modeling diffusion of nutrients and growth factors in biological tissues. Modeling the diffusion of nutrients and growth factors in biological tissues involves following the partial differential equations that describes how these substances move and react within the tissues. A typical approach is to use Fick's second law of diffusion, which can be expressed as in equation number 1. So here you can see this is the del C upon del T is equal to d del square C plus RC, where C is the concentration of the nutrients or growth factor, D is the diffusion coefficient, and RC is the reaction term that represent consumption or production of the nutrient or growth factor. The above equation can be reduced in the one-dimensional model. The equation simplifies to del C upon del T is equal to D del 2 square C upon del X square plus RC. The PDEP function in MATLAB is designed to solve the partial differential equation, which is the most general equation, and we will compare these two equations. So while comparing, we can see that the value of this coefficient, which involves x t u del u upon del x, is equal to 1, and here the value of m is equal to 0. Then we have the equation number 2, and also the coefficient f involve only del u upon del x with this one. So and also the value m specifies the symmetry of the problem. When we have m equal to 0, then we have the slab symmetry. When we have m equal to 1, in that case we have the cylindrical symmetry, and m is equal to 2, then we have spherical symmetry. But in the present problem, we have m equal to 0, which means the slab symmetry or Cartesian coordinate. After that, we have to define the partial differential equation in the MATLAB by comparing the coefficient, and this will help you. We have to write initial condition function and boundary condition function. Then after, we will use MATLAB for the required domain, and we have the visualization results by using the MATLAB. So first we have the defined partial differential equation, C, F and S, as we discussed in the previous lecture. If you did not attend, you must see the previous lecture. This will help you for the more understanding about these functions which we have defined in the MATLAB. So C, F, S are the coefficients, and we save this partial differential equation with the name of diffusion PDE. X, T, U and du dx, these are the input argument, and C, F, S, these are the output functions. We have D is equal to 1, this is the diffusion coefficient. R is equal to minus U, W, which is the reaction term, and the value of C we have is 1, and that of F we have is D into du dx, and value of S is equal to R. So this is the first part of the partial differential equation, which can be easily we can define in MATLAB, and the same code will be saved in the MATLAB, and then after we will call these functions, and I will explain in the complete details how you can use this code. Second, we have the initial condition. Here we need to define. So this is the initial condition U naught. U naught means when t is equal to 0. Okay, so this will be equal to U, X and 0. So the diffusion IC, this will be the name of the function and will depend only on X. Here the initial condition we are choosing here, exponential function is exponential function of minus x square. Okay, later on we can have a sine function, cosine function, logarithm function. Any function can be here at this place. We can manipulate according to our requirement, and we will save this file in the MATLAB. Then after we need to create one more function, which is boundary conditions. So here, as you know, in the previous lecture we all discussed in very complete detail, but here we have the very small description here. So we will save this file with the name of diffusion BC. These are the input argument XL and XR. These are the left domain of X, and this is the right end. UL and UR, these are the functional value at these boundary values. T is input time, so these are the input arguments, and PL, QL, PR, QR, these are the output arguments corresponding to these inputs. So PL will be equal to UL, left boundary condition, and QL will be equal to 0. Initially we are supposing here the coefficient left boundary condition is 0, and PR is equal to UR, this is the right boundary condition, and QR is equal to 0, the coefficient of right boundary condition. Initially we are supposing here 0. After writing this code, we will save the file in the MATLAB with the name of diffusion BC. Here we are defining the spatial domain and time span by using this sequence of statement, and we will call the function, and we can easily visualize the result. So how? First we have the X is equal to linspace minus 5 to 5, and we discretize this domain into 100 points. So this is the spatial domain, and for the t is equal to time span, which is defined as linspace. The interval we have is 0 to 2, and we divide this domain into 50 points. To solve this partial differential equation using PDEPE, we need to call the function, and here you know m is equal to 0, slab symmetry. So this is the solution. This statement will return the solution of the entire function, and which we need to call at this place. This is the inbuilt function PDEPE in MATLAB, and we need to give here input in the same pattern as we discussed in the previous lecture also. Here is first we have the m, then we are calling at its place diffusion partial differential equation. At the rate we are handling these functions which we define in the user file. Okay, then we are handling the diffusion initial condition, we are handling here diffusion boundary condition. This is X and T. So this statement will solve the partial differential equation with its initial condition and boundary condition. Then we need to extract the solution, and after simplifying we will store in U. This statement will save all the values for U, and solve is the solution which is stored here, and first column, second column, these are used for X and T. Okay, so all the values will be stored in this statement. Then after we are using here the plot statements, and we are using here surface function. So this is the surface function, surf X input, T input, and U. This is the title, a concentration of nutrient growth factor over time and space. This is the title. Then we have the X label, spatial coordinate X, and on Y label we have time T, Z label concentration C, and shading interrupt. So when we will execute all these sequence of statement, these will visualize the result. So let's see in the MATLAB. So now you can see this is the MATLAB, and this is the main source file. This is the main source file, and by using this file we can easily visualize all the results. Okay, and you can see this is the main partial differential equation. The statement which we discuss in the presentation are the same. Just you will save the file with the name of diffusion PDE. These are the input argument, and the name of the file must be same as at this place we define here, and you can see here also. So this must be same as we have a function for partial differential equation. Similarly, we have this. This is the boundary condition. Sorry, initial condition, and this is the boundary condition. Okay, and these three functions are important. We make it easy, and all these are user defined function, and here we will call all these functions. You can see these are the spatial domain and time span. Okay, the value of m we choose here 0, and solution PDEPE. These are the same statement as we did PPT. Okay, and after that we need to extract by using u is equal to solution. Okay, and when you will execute this sequence of statement, either you can press F5 or you can press directly at this play or run icon. So when I will press here, this is the output file visualization of the inputs, the solution of partial differential equation for on the top you can see the title, concentration of nutrient, growth factor over time and span. On the horizontal lines, on the one dimension we have time t, and the other we have spatial coordinate, and the on vertical line on the left side you can see concentration C. From this place you can rotate in any direction. For more understanding according to your choice, you can rotate this diagram at 360 degree. Okay, now if we have at this place C is equal to, I am choosing 10. Okay, first you need to save this value for manipulating these parameters. Okay, then run the code. You have this visualization. For manipulation you can make changes for different values. This is corresponding to when we have C is equal to 10, and if you make more changes, D is equal to so I have 5. First you need to save this file. Okay, then come here, play the code. So you will have this visualization. You can see here according to the input argument we have the corresponding change in this diagram, and you can easily interpret the result by comparing with the previous. Okay, and after that, if you want to change the initial condition, here we have exponential minus x square. If I make here sine function, then first I need to save, and then I have to run the main file which is saved with the name of example1, and you can run the code. So here you can see the corresponding result in this file. So this is the result you can see. Okay, if you want to save this file in your MATLAB for the output, okay, just you need to press Control S, sorry. By pressing Control S you can save the file, and this is figure 1.jpg. I want to save this file with extension JPG, and then enter. So the file automatically saved in our current directory. You can see here this is the file. I have another way to use the same code, and here in the single file we have everything. You can see at the top we have X linspace, spatial grid, then we have the time grid. These are the parameters. D1 is equal to diffusion coefficient for one example, and this is the second. So here we will plot two different graphs. Okay, D2 is 5a minus 3. M is equal to 0, and this is the solution, and solve for the first set of the parameter u1. So there will be two solutions. One is u1 and other is u2, and you will save here at the rate PDE function 1, and here is PDE function 2, since two solutions are there. Okay, for different solutions we are saving two different functions. Then after we have the plot function. You can see here this is the first plot function, and then we have the second plot function. Okay, so here you can see this is the first function PDE and this is the second function PDE. Okay, and the initial condition and boundary conditions remain the same when you will execute these sequence of statement, as you can see, and the entire file is visible to all of you very clearly. Okay, once again you can start from this one, the function statement, which is tissue underscore diffusion, and this is the entire code. You can clearly see here till the end. This is the end of the function. When you will execute these sequence of statement in the single file, press from this place, and you can see we have two different plots are there for different input values. So this is the, on the left side we have first diffusion with the d is equal to 1e minus 3, and on the right hand side we have diffusion with the d is equal to 5e minus 3. In conclusion, modeling the diffusion of nutrients and growth factors in biological tissues using Fick's second law and MATLAB provides essential insight for application in tissue engineering, drug delivery, and cancer research. By following the outlined steps, you can effectively set up and solve diffusion problems, enhancing your understanding of these critical process. Thank you for your attention, and I hope this session has been informative and useful.